Hey there, welcome to a video discussing pages 2 and 3 of the section 7.1 notes. So here we're going to discuss an initial value problem. So let me read the little blurb here. For first order differential equations, we find a particular solution as opposed to a general solution like we did earlier in these notes if we're given the value of the function at one point. So let's solve the following initial value problem exactly. So here we have dy over dx equals 3 raised to the x power times natural log of 3 plus 3 times root x. And you're told y equals 0 when x equals 0. Okay, great. So remember what we do. We separate dy and dx. So dy equals parentheses 3 to the x power times natural log of 3 plus 3 halves. We'll make that times x to the 1/2 power and then times dx. So we separate the differentials there, right? Then if we think about it, if we take the integral of both sides, remember that's what we're trying to do here. We integrate both sides. Then you should get y equals, and that's just going to be 3 to the x, because root of 3 to the x is 3 to the x times natural log of 3. Here, remember, we add 1 to the exponent, so it comes 3 halves times x to the 3 halves. We divide by the new exponent, which of course is 3 halves, and those cancel. And of course, you got plus c. Now I'm going to have to use a space down below because I'm running out of room here. So now what you're going to do is you're going to plug in 0 and 0 for x and y. So 0 equals 3 to the 0 plus 0 to the 3 halves power plus c. So 0 equals, remember, 3 to 0 is 1 plus 0 plus c. Therefore, c is -1. So therefore, the exact equation for y, given our initial value for when y is 0 and x is 0, is going to be y equals 3 to the x plus x to the 3 halves power minus 1. So far that seems pretty straightforward. Now what do we do if we cannot come up with an explicit antiderivative like we just did for example 5? So let's take a look at example 6. So dy over dx equals square root of 1 minus e to the 4x. And here you're told that y equals 7 when x equals -5. And you're asked to use an integral expression in your answer. So we haven't really done an antiderivative like that, and that's just really hard to do, actually. In fact, I don't think you can do it analytically. But drum roll, we can use the fundamental theorem of calculus. Now remember what the fundamental theorem of calculus states. It's telling us that if you take the derivative of some integral, say from 0 to x, of f of t dt, because it's f of x. And we're going to use, by the way, FTC part 1 here, not part 2. Part 2 is when you're evaluating a definite integral and you plug in the limits of integration to the antiderivative. We're using FTC part 1, which I have written red right here. So if I utilize that kind of concept, then what I could say is that, when I have dy over dx, so again, I could separate dy and dx, right? And if I were to, or actually, let me backtrack a little bit. We're not going to separate dy over dx. My apologies. Let's backtrack. Please erase that. So here's what I'm going to do instead. I'm going to write d dx of y equals the square root of 1 minus e4x. Okay, so I'm deliberately pulling that y out from the d dx. So same thing, dy over dx, dx of y, same thing. So I'm going to deliberately let y equal. I'm going to deliberately let y equal the integral from -5 to x of the square root of 1 minus e4t dt. Why am I doing that? The reason why I'm doing that is because if I do take the derivative of this, if I do take the derivative of this y here with respect to x, well, what is all that going to be? Remember, you have a constant and you have x up top. That's just going to be root 1 minus e4x. which is what we had for dy dx. So essentially, I could rewrite this whole thing or I could supposedly let y just equal the integral from -5 to x of square root 1 minus e 4t. So essentially what you're doing is you're replacing the x with a t, and you're writing an integral where you're using this as your lower limit. And the reason we want to use that as our lower limit, and then one other thing we have to do as well, we have to put a +7 here. That's one little extra thing we have to do. The reason why is that if I were to plug in -5 into x here, of course, and the lower and upper limits are the same, the integral becomes 0, and therefore y is 7 when x is -5. Also, the fact that if I were to take derivative of both sides with respect to x, if I were to take derivative with respect to x, you get dy dx, which we get. You do dx here, and what happens is that the derivative of 7, of course, goes away. It's a constant, and the derivative of the integral is part of FTC part 1, and it just comes root 1 minus e4x. So it's a little bit weird. We'll talk more about it in class next time we meet, but that's what you would do. So let me kind of remove that, and that answer is what you get in blue. So there's not really much work you have to do, it's just more writing than anything else. Another thing I want to talk about that can be a little complex are these initial value problems when you have a discontinuous solution. So what that means is that sometimes when the general solution has more than one branch, so meaning like if you have like y equals like 1 over x, for example, let's say that was your general solution to a differential equation. So you get these two branches here, right? Because it's a rational function. Then we need to restrict the domain for our solution to a particular branch that contains that initial value. Like, let's say your initial value is at like 2, 1/2, because that satisfies this equation, obviously. Then, of course, you got to focus on this branch then. So it means we have to restrict the domain and say, hey, our domain is going to be x is greater than 0. So it's something you have to be mindful about when you're doing these problems. So for example, let's look at example 7. If I were to just, now we kind of know that we're doing the antiderivative, right? It's just not so hard anymore. So y is just simply going to equal, that's going to be 2 secant x, because derivative secant x is secant tan x. And then remember, we just add 1 to x, 1 divide by a new exponent. So it's going to be minus x cubed plus c. Take derivative just to prove yourself that's what you get. Plug in -1 for y and 0 for x. Of course, you solve for c. -1 equals 2 plus c, so c is -3. Great. So we could say our equation is y equals 2 secant x minus x cubed minus 3. Great. Here's the problem, though. Secant is not continuous for all real numbers. In fact, secant has some breaks. Like, cosine we know looks like this, right? That's cosine. Secant is when you draw these little asymptotes wherever cosine crosses the x-axis, and you have to draw these kind of little U-shaped things. You might remember that from pre-calculus. That's secant, and I could erase this red curve in the middle here. So that's secant. So you do have these breaks. In fact, the breaks happen, or this continues at pi over 2, 3 pi over 2, and so forth. Well, 0, -1 is clearly going to be in this branch right here, between -pi over 2 and pi over 2. So we will have to restrict our domain here because obviously this is not continuous, and we want this to be continuous to make sure we could find the derivative. So you would have to kind of specify what interval you're dealing with. So you'd have to, just as a little extra thing, just say that, oh, by the way, this is between -pi over 2 and pi over 2. So I would advise you to graph or use a graphing calculator Desmos to see where this is going to be defined. And of course, choose the interval where 0, -1 is included. I didn't graph it in Desmos because I just kind of knew that that's where we're going to have a problem, is that pi over 2 or 3 pi over 2 or 5 pi over 2 or 7 pi over 2, -pi over 2, -3 pi over 2, and so forth. So I just chose the domain that contains 0, -1. Here's one more example, and we'll end the video. So one reason why we need to restrict the domain when our solution is a function with separate branches. So let's look at 1 over x. The derivative of that is easy. Remember, 1 over x is x to the -1 power. So the derivative is going to be, oh goodness, can't write these days, -1 times x to the -2 power, or -1 over x squared. That's our derivative. And here are the graphs. Obviously this is 1 over x off to the left. Off to the right is actually going to be a piecewise function, 1 over x plus 5 when x is less than 0, and 1 over x when x is greater than 0. Now, in this case, if you do the derivative of either this or this, you do get the same thing, -1 over x squared. Now, suppose you're asked to solve the following. Find the particular solution to this differential equation. Now, remember, f of x was just 1 over x straight up. The derivative was -1 over x. G of x was a piecewise function, where it had 1 over x plus 5 and 1 over x. Obviously, 1 over x plus 5 when x is less than 0, 1 over x when x is bigger than 0. That also gave the same derivative as f of x. So when you're asked to solve that differential equation, you have a bit of ambiguity, because would it be 1 over x, or could it be some piecewise function? We don't know. And if you're talking about, hey, solve this differential equation at 1, 1 is your initial value, well, 1, 1 is on both of these here, but clearly these are both different functions. So you do have a problem, because you have that ambiguity, because sure, you could solve this differential equation and say, yeah, the answer is 1 over x. Well, who's to say it couldn't have been a piecewise function? Because there's another branch that could have done something else. So both f and g pass through 1, 1, both have the same derivative. And we can make up infinitely more functions like g, like we could say 1 over x plus 10, 1 over x minus 4, 1 over x minus 20. So the only thing we know for sure about our solution is that the right-hand branch is correct. So we give our solution with a restricted domain. So you still say 1 over x is fine, but you have to add that domain that x is greater than 0 when you solve this, because you have no idea what's going on in the left branch. So you have to be mindful about that. So we do have to restrict our domain in our answers. And on the AP exam, if they do this as potentially a free response problem, they would probably dock you if you didn't say the domain. Not a big deal, because when you solve differential equations, most of the stuff you do before you isolate or solve for y, you get points for all the other stuff, like separating the differentials and integrating and finding c. So that's just the algebra part. They only give you 1 point for that. So it's not a big deal if you forget about it, but you just got to be aware of that. And next time we'll talk about graphing general solutions when we meet again as a class. All right, thank you.